Espresso Talks by Sphere Energy.
Welcome everyone to our new episode of Espresso Talks. Today we're going to focus on a very important topic, really the frontier of engineering, which is physical AI. And I quickly introduce myself. I'm Gianmarco Gabrieli and I'm leading the AI team at Sphere. And today we are broadcasting in our Munich office with Oliver Schilter, our lead AI architect. So we are gonna dive a little bit into the topics related to physical AI and what this means for engineering workflows. So to start off, Oliver, what do we mean exactly when we say physical AI?
Right, that's an excellent question, right? Nowadays, most people are familiar with chat bots like ChatGPT or other LLMs that are mainly focused on the language as a modality. So you interact with the chatbot through language, but a lot of problems we face in our daily engineer lives in classical engineering are not in the modality of language. So there's a lot of other modalities that we need, for example, time series data or CID parts and so on, that cannot be directly put into an AI model like ChatGPT or so on. So if we talk about physical AI, we want to have an AI that really understands the real world connection between physical phenomena.
Right, and this is very important that, for the first time we try to bridge, let's say, the data-driven approaches to, the really physical world, but also following the physical rules, as you mentioned. But then, don't you feel there is a little bit of a contrast, right? So from the classical way of dealing with this kind of data, with the physical laws, and the actual, fully data-driven approaches. So how do you think this can be reconciled together?
Right, if we talk about classical simulation, we usually talk about numerical simulation that follows predetermined set of equations that usually are governed in some physical phenomenon, like a temperature law or interaction between particles and so on, that are modeled according to mathematical equations. And the benefit of this is that each of your model behaves exactly as you determine in the equations, but the fundamental problem is that you have to solve them, and solving them is very, very expensive computationally. So lastly, we like in the recent year, we come to the conclusion that we can maybe approximate these very expensive equations with data-driven models. The problem is with data-driven models is that they learn what they were trained on and often don't generalize well out of the training data. This can lead to the fact that it maybe performs in a data-driven model that approximates this physical simulations, works very well in the distribution it was trained on, but then horrifically fails because it doesn't understand actually the physical laws underlying it. It just learned the pattern in the data.
Right. So I understood, there is a lot of, let's say, considerations to take into account also when we want to develop these kind of models, right? So you need to be aware of both worlds. You need maybe to interact with physicists or, real engineers that know the actual laws or the truth, but also we need a lot of expertise in AI and data-driven models. So thinking about Sphere, right, and what we are doing here together with the team, what do you think will be the most important assets to develop? Like, what will be the ideal roadmap for any company that is, trying to develop assets in this direction?
So, right, our strategy is to develop AI models that follow these physical laws, that have a component in their architecture that kind of grounds these models that we develop here at Sphere in the physical law while benefiting from the data-driven approach. So they learn from the data, but they are governed by physics. So they cannot go and learn, like, let's say, a temperature dependency because it's already baked into them in the model architecture. So here at Sphere, we really value these kind of assets that we want to develop that, for example, then can surrogate these very expensive simulations by data-driven methods that is way cheaper to run. This allows basically to screen also way more parts. For example, we couldn't screen, instead of 2-3 variation, because it's expensive to run. We can run hundreds of them because they are cheaper to surrogate for. So maybe a question for you, Gianmarco, how you see such the model scale in like a infrastructure point of view? How can we make sure that these models then actually perform well at a client?
Right. So I think that's a very important topic, but I feel like in a way, as you said, the computation itself or the compute power is not maybe the main limiting factor when we, just compare to classical approaches of dealing with these, kind of challenges. As you say, classical simulations still require a lot of, hardware and computational power. But the idea indeed with this kind of models is to surrogate some of these tasks. And this means, I believe, like computation is not the main limiting factor, but being closer and closer to the engineers that work then in a company, I feel the problem will be more associated with the interpretability or explainability of these models. I think this is very important when we develop and deploy to make sure that these kind of models do not deliver just an output, just a number. They need to explain why that number is there and is predicted by the model, because this is, I think, the only way that we make sure adoption can be driven in this realm. And of course, I think that the real problem is also that when we think about AI, there is always the easy correlation with the language domain, with the LLMs and chatting with the chatbot. It's very easy to interact and also get feedback. You also, in a way, feel reassured, and you ask maybe questions about daily life. You get answers that are plausible. But for these kind of models, right? So as you mentioned a lot, like the physics-based component of it, I believe like there is the additional challenge that the user needs to be able in these companies to trust the tool also while interacting with it. So not only the problem of, as I mentioned before, making sure that everything that is predicted is explained, but also I feel it could be more like a general problem about, interacting and making sure that also these kind of models don't hallucinate as the language models do, because for the language models you can clearly say you are wrong, but maybe to such tools that might be very sophisticated, you may not know that it's true or not. So you don't know if the hallucination is there, even though it's at a different level. So I think there are a lot of these considerations baked into the question about scalability. But I think this is this part of the let's say of the problem or the conceptual development of physical AI. But then, I mean, getting back to the track of then these kind of models and how we can serve them and so on, where do you think we stand nowadays when we talk about these models? Is the literature or research in an advanced stage? Are we there? Can we really help engineers today, or do you think there is a gap?
As we can see that an engineer is not just one person, right? It's a whole team, a whole process. And we have several models that definitely help an engineer on the day-to-day business in very isolated cases. So if we walk along, let's say, a classical engineering workflow like the V setup, where we start from requirements, there we have, say, it's not physical AI, but we can do a large language model, we can do information extraction, requirements tracking, and so on. And then if we go along it, if in the development process, we actually have a lot of physical AIs that maybe help us to evaluate a part on simulations more quickly. We can validate, so on. And this already helps a lot the engineer on their day-to-day business. So I think we are in the adoption phase. Regarding the research state in physical AI, it's a fast-moving field. So there's a lot of advancement ongoing because the people actually see the importance of grounding your models, your data-driven models in real-world physics, because this goes back to what you said. This actually then also gains trust in the engineering mindset. So the cultural trust of an engineer, that he trusts the solution because he knows the model follows this certain set of equation that he knows from the classical field of engineering very well and use years and years before. So this actually helps a lot in the engineering day-to-day.
Cool. Yeah.
So we talked a lot about like data and what kind of data is needed. What is your biggest opportunity regarding like here in Europe regarding, let's say, company and their data? How can they use it in this context of physical AI? How can they make sure that the data is in a format or ready to be consumed for such models?
Right. So I think you're touching probably on the biggest point here, maybe the biggest challenge. And also, maybe I feel like this is really the gap to make sure that we can really deliver these kind of solutions and make sure adoption is fully achieved. I think for sure, and what we see a lot, I think, while interacting with the clients or different stakeholders in this field, also engineers, we see that a lot of this data is still nowadays scattered and not very well consolidated or, let's say, AI ready, right? So I think this is really the biggest challenge that companies face nowadays. And I feel sometimes there is a fear that, this is like something that can never be reached or achieved. But I think this is really a false myth, because also when interacting with even the engineers, they know exactly where their data is, they know exactly how their process went. And so I think if it starts really from let's say, encouraging the people that actually produce the data to make sure that this data can be in the right format, then I think there should be an overall strategy in making sure that this data is consolidated into a unified data layer. That's how we call it, so that is AI ready, let's say. And then the interaction with the models is the next challenge, right? So assuming that the data is ready, where is this model running? Can I really just provide all my data to any service or AI model, like if, it was just a sentence or a question that they ask? I think the situation is very different, because most of the time these data actually contain the real IP of the company, right? So engineering data is the gold mine really of a company and all the history around it. So I think probably what needs to be done is also, and this is more maybe on our side, to make sure, that if there are companies that want to keep their data, try to make sure that these kind of models can also run within their infrastructure and that is deployed locally, so that if there are data that really cannot be outsourced, then at least they can still be used for this kind of modeling approaches. So I feel this is more like the challenge in the data space, but also how I believe the trend will be in the next years in try to consolidating all of this. Yeah, so that's my take. What is your take?
I think again, right, the issue is almost you mentioned it before, that this engineering data is like the crown jewel of a company. It's where all the knowledge is, where all the details, and also where they differentiate from other competition in the same space. So it's very important that they have the sovereignty of this data and don't outsource it willy-nilly to other, let's say, services and so on, because there is the knowledge. If you have a leak there, you leak basically the whole company's IP. So on the other hand, to be very, very conservative and not do anything with the data is also a missed opportunity, and you get left behind after like 5-10 years, because if the competition uses more advanced models to accelerate their engineering process, they accelerate all the progress, right? So it's important to balance this. So we here at Sphere believe a lot that you should be the owner of your own data. It's not Sphere's data, but we help you train the model in your infrastructure that you can use, and don't lose access to the advancements of AI models, but also not lose access to your data and have it uncontrollably shared with all different providers. You asked me before about like the current state of the field, right? How you see the engineers work today, but maybe if you go like 5 or even 10 years into the future, where you see like these physical AI models really accelerate the engineering workflow or the potential they have?
Right. I think this is basically probably like the answer that combines everything that we have discussed today. And I think a lot of this we are already seeing right now, because you mentioned, probably in 5 years it will be quite different. But I think there is already a trend nowadays in companies and also the engineers' work that, basically show that there is really a transformation happening as we speak right now. And this starts really from the individual engineer or workers that is starting to use probably not all the physical AI models that we mentioned, but already, with language models. Each of them is maybe trying to see whether there is a way they can be supported just by, interacting with the tool and then reiterating on an idea or on a concept. It really helps development and engineering itself, right? It's very interesting. I feel that this is really coming from the natural desire of people of evolving in this direction. So it's not a mandate, that they have been asked to. But at the same time, I feel like there is the challenge, but also the beauty of all of this is making sure that these kind of workflows are not siloed and are not specific to an engineer only, but can also be shared across many, engineers or many people working on same projects or similar projects even, because I feel sometimes there is the problem that, the knowledge stays within the engineer. There is no learning from the past that is, really translated or, let's say, passed to the next colleague. If there is a new engineer, how do we make sure this, engineer is aware of the challenges, what happened in the past, and so on. So I think we probably need to start, as you mentioned before, and this is what I see in the future, that, anybody, even if it's a new joiner of the company, will understand for a specific process everything that happened in the past, all the challenges that there were, what will be already solutions that were developed, that 80-90% of the solution maybe is already there, and with your engineering intuition, you should then fill that gap with the 20%, to make sure that that process is then really suited for your specific application. So I would hope that there is this kind of complementary support between the past, the learning, simulation with surrogate physical AI models, and engineering intuition that will make possible to speed up processes, but also make sure that that process is known by the engineers or many companies, let's say. This is how I feel. But do you have any different perspective, or what do you think maybe would be a day at work for an AI or maybe like physical engineer working in these companies?
I think you mentioned already the overall workday will change from let's say more agentic workflows from language domain, but then they will go into the physical domain, where it's like, for example, retrieving similar cuts on physical aspects, running simulations more exhaustively because of the surrogate models that you have, and also trusting the models again, right? Because we know they are grounded in physics, they behave as expected. If you go, say again, to a different temperature range and so on, to really have the trust in the physics that is underlying the AI model, as well as you mentioned it before, let's say the knowledge transfer should definitely improve through this, because this then kind of formulates these processes also more structured, and from this structured process you can learn as a new engineer quickly and understand why let's say the previous engineer maybe did something that you do now the same or in a different way.
Right. I think this is a very interesting point of view, and I think we all look forward to really see what we are saying, how it would be translated if the adoption would really thrive in the way we expect. I think there is very high chances, and I hope today we also convinced listeners and watchers that physical AI is really kicking in more and more every day, and every year we see a lot of developments in this direction. So yeah, we look forward to seeing that future coming. So having said that, thank you very much for watching and listening today, we'll see you in the next podcast and Espresso Talk episode.